Okay, Assalamu alaikum. Everybody listening? आवाज आ रही है? आवाज आ रही है?
Yes, yes, sir.
Okay. इसको बंद करते हैं. So let me start sharing the screen. इसको किया. Okay. Okay. तो last time जो हमने किया था, what was that? अरे admitted. Okay. तो हमने किया था शायद, हाँ, we had done something about the quotient space. If y is closed in X, a subspace, then X by Y is also a normal linear space. ये हमने किया था कोसेट नॉर्म से related. Okay, now we can go further with that actually. कुछ चीजें हैं जो तुम्हारे नोट्स में हैं, कुछ एक्सरसाइजेस वो कर लेना. अभी फिर मैंने कहा था we are looking for, we know something about the linear maps between two linear spaces, homomorphisms. Then we also know about, X is, when it's a normal linear space, it's at the same time a metric space. So X is a normal linear space, means it's a vector space, a linear space, vector space. It's also a metric space, topological space. So we can talk about continuous functions as well as linear functions. So there is an important theorem, which is the characterization of linear maps that are continuous between two normal linear spaces. उससे related एक theorem है जिसको हम बहुत use करेंगे इस idea को. So let me write it down. Let X and Y be normal linear spaces over some field K linear spaces, and T be a map from X to Y with a linear transformation. By that I mean that homomorphism जो तुम्हें पता है. It's a linear transformation. Then the following are equivalent. Then the following are equivalent, one implies the other. Then the following are equivalent. Pehla, T is continuous. Second, T is continuous at the origin. Origin means the zero element of X in the sense, in the sense of the metric space. That is, if Xn approaches 0, T of Xn approaches 0. Third one, this is an important one. There exists a positive real number, a K positive, such that with the property, the third wala, isko 3 likh lo, not third. with the property, अभी दो हैं waiting room में और time पे आया करो ना. Okay. With the property t of x in norm is less than equal to k times norm of x. Of course, the fourth one is if S is the unit closed ball, means all x belonging to x such that norm x is less than equal to 1, then its image is the closed unit ball in x. इसमें बहुत सारा आ गया. Of course, I would explain. Then its image t of s is a bounded set in Y. So ये चार चीजें मतलब इक्विवेलेंट है, यानी अगर हम एक को मान ले तो बाकी तीन भी सच है, और कोई भी एक को मान ले तो बाकी तीन भी सच है automatically. So that's what we're going to prove. We're going to show that 1 implies 2 and 2 implies 1, 2 implies 3 and both are equivalent. Now important जो है, अगर हम पहले पे ध्यान दें कि t is continuous. T would be continuous everywhere if it is continuous just at the origin. पहला ही कह रहा है ना, अगर ये दोनों बराबर हैं तो अगर t के just origin पे continuous है एक ही point पे, in fact it could be any point, चलो origin is the convenient one, so then it is continuous everywhere on x. Second one, और ये जो third property है कि it is continuous if and only if t of x is less than equal to some k times norm of x, which means that basically it says that if domain is bounded then range is also bounded. Same is the idea with what is the fourth one? The unit ball जो है, unit ball means all vectors of length less than equal to 1. Then its image is also a bounded set under a linear map. Okay, so let me go to the next page where I will explain it. Okay, so proof. Let's first show that 1 is the same as second. So 1 क्या था हमारा? T is continuous. ये 1 है अपना और 2 है अपना. T is continuous at 0. T is continuous का मतलब T is continuous everywhere on x. Now the important thing is, since T is linear, if it is continuous just at one point, that's a very important thing about vector spaces, that addition gives us the power of translation of open sets, and under translation open sets are open because addition is continuous. So you just have to worry about the continuity at just one point. If that is true, then the function, the linear map must be continuous everywhere on a vector space. Well, of course, that's not true for a general topological space, general metric space. It's only because that we have that power of addition and scalar multiplication with us. And it is important because that we are defining, because T is linear in the first place. ना? उसकी वजह से अगर 0 पे continuous है तो हर जगह continuous है. Okay. अगर t continuous है तो फिर 0 पे भी continuous होगा. One way तो easy है ना? 1 implies 2 is obvious. क्योंकि अगर continuous है तो हर जगह continuous है, तो in particular origin पे continuous है. Now 2 implies 1 कैसे होगा? Now suppose that t is continuous at origin. We have to show that it's continuous everywhere. Let x belong to x. And let x belong to x. Okay. Then such that xn is a sequence inside x and xn converges to x. So अगर xn converge करता है x4, you have to, यहाँ जरा ध्यान में अगर रखूं, in normal linear space, when I say xn converges to x, I am basically saying that xn minus x, this thing, this real number, converges to 0. Right? So I can say then, in fact, I can do further. So it means that, to admit, xn minus x converges to 0, 0 vector, right? Because 0 can be written as, और चूंकि नॉर्म कंटिन्यूअस है तो इसका मतलब xn minus x converges to 0. So xn minus x converges to 0, but t is continuous at origin, है ना? Now since t is continuous at origin and it's a metric space, it implies that t of xn minus x converges to t of 0. But since t is 0, it means that since t is linear, it means that t of 0 is 0. A linear map, the homomorphism will always send 0 to 0. Now this is 0 inside x, now this is 0 in the range. That's fine. Also t is linear, then I can write t of xn minus t of x converges to 0. And since addition is continuous, it implies that t of xn converges to t of x. So we started with xn converges to x, we got t of xn converges to t of x, which means that t is continuous at x. And since x was arbitrary, and since x was any element, any x is arbitrary, then so t is continuous. So we got 1 is equivalent to 2. Okay, admit. Okay, ये तो हो गया 1 is equivalent to 2. Now let's come 2 is equivalent to 3. And if it is continuous at the origin, then we must have norm of tx. Oh, 1 minute. Okay, so अब मैं यहाँ फिर से लिखूंगा what is 2 and 3. 2 है t is continuous at origin. 3 है अपना कि norm of tx is less than equal to some k times norm of x, where k is some positive real number for all x belonging to x. So we have to show that 2 and 3 are equivalent, right? So suppose that, पहली बात तो ये है कि 3 implies 2 is obvious. तो मुझे दिखाना है 3 is equivalent to 2. Now 3 implies 2 is obvious. Why? तो मुझे बताएगा. Because अगर 3 सच है ना, और xn converge करता है, अगर 3 सच है कि t is continuous at क्या बोलते हैं origin, so it means that अगर xn converge करेगा 0 को, तो t of xn would converge to t of 0. That is the same thing as 0. Okay, लेकिन अगर t सच है, अब अगर t true है, अगर 3 true है, तो उसका मतलब क्या है? t of xn, चूंकि हर x के लिए true है, so it is less than equal to k times norm of xn. So अगर xn converge करेगा 0 को, तो t of xn would also converge to 0, which means that t is continuous at the origin. So 3 implies 2 is rather obvious. क्योंकि अगर xn, because then t of xn would converge, क्या मैंने कहा? Because then t of xn is less than equal to k times norm of xn. So if xn converges to 0, ये तो उससे less ही है और non-negative है, तो this must also converge to 0. So 3 implies 2 is obvious. The question is, does 2 imply 3? Now to show that 2 implies 3, now suppose t is continuous at 0. Now we have to show that, हमें क्या दिखाना है? that there exists some k positive such that norm of t of x is less than equal to k times norm of x for all x belonging to x. तो हमें ये दिखाना है. Oh, assume to the contrary. It's not true. Assume to the contrary. मान लो ये सच नहीं है, मतलब जो हम प्रूव करना चाहते हैं. Assume to the contrary, this is not true. उसका मतलब क्या होगा? उसका मतलब ये होगा कि ये सच नहीं है ना? So assume to the contrary, no such positive number exists. No, assume to the contrary, no such k positive exists. Then, for each n, each natural number n, we can find, n is a natural number, of course, we can find some vector xn such that t of xn is strictly greater than n times norm of xn. Of course, norm of t of xn. तो देखो मैं क्या कह रहा हूँ, मैं कह रहा हूँ सपोज दिस इज नॉट ट्रू, तो उसका मतलब क्या हुआ कि यू कैन नॉट हैव t of x is less than equal to norm of x for all x. ये सच नहीं हो सकता, ये भी सच नहीं हो सकता, है ना? ये भी सच नहीं हो सकता क्योंकि ऐसा कोई नंबर है ही नहीं, ना ही 1 ना ही 2, कोई भी पॉजिटिव नंबर नहीं है ऐसा हो सकता जो इस इक्वेशन, इस इनइक्वालिटी को सही माने, क्योंकि हम मान रहे हैं ऐसा कोई की है ही नहीं. सो इसका मतलब कम से कम एक x होगा such that t of x is strictly greater than norm of x. कम से कम एक x ऐसा होगा कि norm of tx is strictly bigger than twice norm of x. राइट, इस वाले x का जो कम से कम एक है, इसका नाम हमने दिया x1, इसका नाम हमने दिया x2. इसी तरह से वो वाला x such that norm of tx is strictly greater than 3 times norm of x, उसका नाम हमने दिया x3. So in general, I can get a sequence of vectors for each natural numbers such that norm of txn is bigger than n times norm of xn. So it would imply that dividing both sides by n times norm of x, so I can write 1 by n times norm of xn, then into t of xn, of course in norm is strictly bigger than 1. Of course, this is true for all our construction, and which would imply using the properties of the norm, and this is a non-negative number, so I can take that inside norm, and since t is linear, I can take them because this is just a scalar. It would imply t of xn divided by n times norm of xn inside t and whole thing inside norm. This is bigger than 1 for all n. For all n. Okay, remember this. That would imply. So then, yeah, let yn be equal to this thing, and let this be x divided by n. Oh, sorry, x divided by n times norm of xn. Then we have norm of t of yn is bigger than 1 for all n. मैंने इसका नाम बदल दिया. But yn, as you can see, converges to 0 as n approaches infinity. Y of n, अगर मैं n बढ़ाता जाऊं तो ये n चूंकि यहाँ पे है ना, so this would actually converge to 0. तो यहाँ पे xn है, sorry. Okay, so yn would converge to 0 as n approaches infinity, and t of yn जो होगा, it cannot converge, does not converge to 0 because इसका norm तो bigger than 1 है for all n, whatever कितना भी बड़ा ले हम. So which contradicts our supposition. हमने कहा था t is continuous at the origin, लेकिन इस हिसाब से तो t continuous at origin नहीं है. This contradicts that t is continuous at origin. So if t is continuous at origin, then जो कि मैं कह चुका हूं कि norm of tx is less than equal to k times norm of x for all x. Okay, now 3 is equivalent to 4. What was 4? जरा मैं देखूं, 3 तो मुझे याद थे. अब 3 क्या है? अब this is our 3. 3 हमारा ये है कि t of x is less than equal to some k times norm of x where x is a positive number. 4 है अपना कि t of s is bounded. कि अगर मैं लूं unit ball t of s where s are all unit vectors, all vectors belonging to x such that norm x is less than equal to 1. अगर ऐसा है, so t of s is a bounded set. Okay, let's go after that. So 3 ये है, 4 क्या है? हाँ. Okay. Now since, so what was 4? फिर से मैं देखता हूँ. Okay. Now 3 implies 4 is obvious, है ना? वो क्यों मैं फिर से एक हमेशा इसमें obvious ही है वैसे. Now 3 implies 4 is obvious. Why? Because अगर norm of x is less than equal to 1, जो कि s के लिए है, s के लिए है ना norm, s की property है कि सभी vectors का norm less than equal to 1 है, then अगर मैं third को सच मानता हूँ, so norm of tx is less than equal to k for all x belonging to s, which would imply t of s is a bounded set. So ये तो obvious. The question is 4 implies 3. 4 implies 3. अब 4 implies 3 का मतलब क्या है? वो भी उतना कुछ मुश्किल नहीं है कि अगर 4 ट्रू है तो उसका मतलब क्या हुआ? t of, okay, मुझे 4 से दिखाना है 3. I have to prove 4 is this and I have to prove this. Now if x is equal to 0, 3 is trivially true क्योंकि दोनों साइड 0 हो जाएंगे. Trivially true. So let x not be equal to 0. ठीक है? x अगर 0 होगा तो t of x भी 0 है, यहाँ भी norm of x भी 0 है, norm of tx भी 0 है, so 0 is equal to 0, nothing to prove. So अगर x 0 नहीं है, अगर x 0 नहीं है, then I can take y, so let x be not equal to 0 and y be equal to x by norm x. Then norm of y is equal to 1, which implies that y belongs to S. And hence, now, and since by 4 कहता है जो हम 4 से हमें 3 imply करना है, तो 4 कहता है t of S is bounded, implies that y S में है, then t of y in norm is less than equal to some k for some k positive. लेकिन y किसके बराबर है? y है बराबर x by norm x के. And using the fact that चलो less than equal to लिखते हैं element. So this is less than equal to k. And using the, because t is linear, तो scalar जो है 1 by norm x वो बाहर आ जाएगा, और चूंकि ये नॉन नेगेटिव है तो ये नॉर्म से ही बाहर आ जाएगा. So I can write, चलो मैं थोड़ा सा तुम्हारे लिए ऐसे कर सकता हूँ, into tx is less than equal to k, which would imply, इसको दूसरे साइड पे ले सकते हैं हम, norm of tx is less than equal to k times norm x for all x not equal to 0. मैंने कंडीशन क्या ली थी? Not equal to 0. लेकिन 0 के लिए तो ट्रू मैंने पहले ही बताया था, क्योंकि 0 के लिए तो trivially true है. Hence I can say norm of x, norm of tx is less than equal to k times norm of x for all x belonging to x. So एक और कंडीशन प्रूव हो गई. Now the fourth one, the last should be 4 is equivalent to 1. What was that? कि नहीं हमें नहीं करना, नहीं जरूरत ही नहीं है, हम तो सारे कर गए है ना. वो तो अगर हम सर्कल में करते तो वो तो खुद ही हो गया. हमने प्रूव किया 1 is equivalent to 2 is equivalent to 3 is equivalent to 4. So अब हमें पता है कंटिन्यूअस होने के लिए क्या काफी है. t अगर कंटिन्यूअस के लिए काफी है कि t is continuous at origin, और सबसे अच्छी बात there exists some k positive such that norm of t of x is less than equal to k times norm of x for all x belonging to x. So if t is a linear map from x to y, then t is continuous if and only if and it is equivalent to this. ये वाला तो हम ज्यादा यूज करेंगे. नहीं, हम ये डेफिनेशन, अब ये डेफिनेशन बन गई ना ये चारों की चार फॉर कंटिन्यूटी ऑफ अ लीनियर मैप. तो अगर लीनियर है, अगर ये लीनियर मैप है तो दिस इज सफिशिएंट to imply that t is continuous, and if t is continuous that this would be implied. We use this definition for the continuity of a linear map between two normal linear spaces. So that's what we would focus on. Okay, so और क्या हम कर सकते हैं, right? T is linear. Okay, तो हम इसको बोलते हैं फिर, मतलब इसकी वजह से बुक्स में तुम देखोगे हम जो कहते हैं ना T is a continuous linear transformation. हम कहते हैं, अक्सर हम यूज करेंगे T is a bounded linear transformation. बाउंडेड का मतलब बाउंडेड नहीं है, ठीक है ना. बाउंडेड का मतलब ये वाली प्रॉपर्टी है. ये लीनियर मैप बाउंडेड नहीं होता, लेकिन बाउंडेड इन द सेंस दैट कि अगर डोमेन बाउंडेड है तो रेंज भी बाउंडेड है, ठीक है ना. लीनियर मैप्स आर नॉट जनरली बाउंडेड बिकॉज वी हैव गॉट अ वेक्टर स्पेस, और स्केलर बाहर आ जाएगा तो उसको अनबाउंडेड कर देगा. So, लेकिन T is continuous linear transformation. Books में और मैं भी कहूँगा T is a bounded linear transformation. By that I mean T is linear and continuous. And by that, of course, I mean T is linear and this, जिसको मैं encircle कर रहा हूँ, this property is satisfied. Is it clear? Is it clear? अब मैं थोड़ा इसको, कोई सुन रहा है मेरी बात? Hello, hello out there. अरे एक
Yes,
play
yes, sir.
ओके, एक मशहूर प्ले है, उसका नाम है हेलो आउट देयर. ओके, सो अब अगर मैं देखूं, अब ये जो है, ये है मेरी डेफिनेशन फॉर कंटिन्यूटी ऑफ ए लीनियर ट्रांसफॉर्मेशन. अब मैं आऊंगा उधर, अगर मैं लूंगा अब होम एक्स वाई, होमोमॉर्फिज्म्स फ्रॉम एक्स एंड वाई. सो इट हैज अ सब क्लास, यानी टी इज लीनियर एंड एक सबसेट है बन जाएगा इसका कि विच आर लीनियर, यानी विच बिलोंग देयर एंड विद दिस प्रॉपर्टी, ठीक है ना. सो वी गेट अ सबसेट बिकॉज वी आर एक्चुअली पुटिंग एन एक्स्ट्रा कंडीशन ऑन इट. एक्स्ट्रा कंडीशन जब हम लीनियर मैप्स पे डालेंगे विच वुड मेक इट कंटिन्यूअस, सो वी गेट अ सबसेट ऑफ दिस होमोमॉर्फिज्म्स फ्रॉम एक्स टू वाई, यानी लीनियर मैप्स फ्रॉम एक्स टू वाई. ओके, तो ये जो सबसेट है, अब हम इसकी प्रॉपर्टीज देखेंगे. नाउ सपोज इस सबसेट में, जिसका नाम मैंने अभी नहीं दिया, सपोज T1 T2 है, वो लीनियर भी है और उनकी ये प्रॉपर्टी भी है. यानी आई हैव गॉट T1, लेट मी कॉल दिस सबसेट A. A मानता हूं मैं, A इज अ सबसेट. Okay, A is a subset which has this property. One thing is clear that T1 plus T2, अगर मैं लूं as a point-wise sum of these two operators, this would be equal to T1 of x plus t2 of x. And using the property of the norm, so this would be less than equal to t1 of x plus t2 of x. अब चूंकि ये इस सेट में है, यानी जिसकी ये प्रॉपर्टी है कि फॉर एवरी x, so t1 की भी ये प्रॉपर्टी होगी, t2 की भी ये प्रॉपर्टी होगी, बिकॉज आई एम सेइंग दैट A इज द सेट, ये A में है और A की प्रॉपर्टी ये है कि t is linear and this property holds. So this would be less than equal to some k1 times norm of x plus some k2 times norm of x, where for all x, which can be written as k1 plus k2 into norm of x. So I would get t1 plus t2 as a sum map, the pointwise sum map. Evaluated x and put into norm is less than equal to some k times norm of x for all x belonging to x. So what does that mean? Where k is equal to k1 plus k2 is a positive number, because k1 and k2 are positive numbers. ये क्या हो रहा है? Okay. What's it? हाँ ठीक है. So it means that अगर t1 t2 a को belong करते हैं, so if t1 t2 belong to this a, then its sum also belongs to this subset of mappings, linear mappings. So because उसकी भी ये property होगी, of course sum of two linear maps is linear, तो ये linear भी होगा और उसकी ये property भी होगी. Similarly, we can show that alpha into t1 also belongs to a for all t, which means that ये जो a set है of the homomorphisms from x to y, यानी a को मैंने define किया है all such things, all linear maps from x to y with an extra property that there exists k positive such that norm of tx is less than equal to k times norm of x for all x belonging to x. ठीक है? So it is a subspace. So A is a linear subspace, क्योंकि अगर दो इसमें हो गए उनका सम होगा और इसके अंदर मल्टीपल भी of homomorphisms from x to y. Okay. Next question है, क्या ये normal linear space है? So now I have, मतलब अब मैं इसका नाम दूंगा क्योंकि अब ये subspace है ना, तो मैं इसका नाम दूंगा bxy. bxy now is a subspace. No, it's itself a vector space. It's a subspace of home xy. अब क्योंकि मैंने इसको नाम दे दिया तो यहाँ मैं रब करूंगा and I will write bxy. Collection of all bounded linear maps. तो मैं words में use करूंगा. Collection of all bounded linear maps from x to y. तो ये होगा हमारा bxy. तो अब ये तो है, अब ये वेक्टर स्पेस है ना, in its own right. It's a subspace of a vector space. It's a vector space or a linear space. So can I define a norm on it? क्या ये normal linear space बन सकती है? क्या ये normal linear space? Can I define a norm? Now remember that what are these? These are mappings. These are linear mappings from x to y with this property. So can I define a norm on them? The answer is yes. Okay. What I do? So I have got now a vector space bxy. I define a norm. So for t belongs to pxy, of course I would use the norm of x and y to help me to define a norm on t. So I define norm of t to be supremum over norm x less than equal to 1 of norm of tx. So remember this is tx कहाँ belong करता है? Y में. So I'm using the norm of y and of course the norm of x to define a norm on bxy. यानी यहाँ norm of t को मैंने norm x में जो already norm था, because x and y are normal linear spaces. तो उसकी मदद से मैंने उसको, पहले तो क्वेश्चन है इज दिस ए नॉर्म, क्या ये सभी नॉर्म की प्रॉपर्टीज सेटिस्फाई करता है। तो पहले तो ये कि क्या ये सुप्रीमम एग्जिस्ट करता है, क्या ये सुप्रीमम एग्जिस्ट करता है। ऑफ कोर्स जो प्रॉपर्टी 4 थी वो कहती थी ये सेट बाउंडेड है, यानी कहती थी ना टी ऑफ एस इज बाउंडेड। टी ऑफ एस मींस टी ऑफ एक्स अगर मैं लेता हूं सच दैट नॉर्म ऑफ एक्स इज लेस देन इक्वल टू 1, ये है टी ऑफ एक्स। तो प्रॉपर्टी 4 जो कहती थी कि टी इज कंटिन्यूअस इफ एंड ओनली इफ दिस सेट इज बाउंडेड, दिस इज अ बाउंडेड सेट। और अगर बाउंडेड सेट है तो इसका एक सुप्रीमम होगा, और उसी सुप्रीमम को मैंने डिफाइन किया। दिस इज अ वेरी इंपॉर्टेंट norm of this operator from x to y, norm of this linear transformation को मैंने उसकी मदद से डिफाइन किया, ठीक है ना। so that's what we are going to do next. We are going to show, let me see, so what we are going to see जो हमारा theorem है, if x and y are normed linear spaces, then bxy, which is the collection of all t from x to y such that t is linear and there exists a k positive such that norm of tx is less than equal to k times norm of x for all x belonging to x. ये सब जो कि वेक्टर स्पेस है, of course is a normed linear space. Under the norm, norm of t is equal to supremum over the closed unit ball of the norm of tx. Let's call it star. Further, if y is complete, y is a Banach space, so is bxy. ठीक है, अब मैं यहां पे थोड़ा तुम्हारे लिए छोड़ूंगा जो मैंने अभी डिस्कस किया। तो इट इज इजी टू शो दैट bxy इज अ वेक्टर स्पेस। मैं सिर्फ नॉर्म की प्रॉपर्टीज वेरी करूंगा, वो मैं वैसे इससे पहले बता ही चुका हूं कि इट्स अ वेक्टर स्पेस, नो इशू। सो नॉर्म की प्रॉपर्टीज भी इजी है वैसे। पहले तो ये कि नॉन नेगेटिव है, क्लियरली norm of t is greater than equal to 0, and अगर norm of t 0 है, it is equivalent to saying, क्योंकि इसकी definition तो यही है, ठीक है, ये तो 0 है ही। Now that would imply t of x is equal to 0 for all x with norm of x equal to 0. Oh, sorry, norm of x less than equal to 1. सभी वेक्टर्स जिनका नॉर्म उनके लिए 0 है, क्योंकि उनका सुप्रीमम 0 है तो सारे का सारे 0 होंगे। But this would imply t of y by norm of y